IT 361 Module 2 Part 1. The name of this module is connectivity. In this module we define two parameters of a graph, its connectivity and edge connectivity, which measure the extent to which it is connected. A vertex cut of a graph G is a subset V' of V such that G minus V' is disconnected. A K vertex cut is a vertex cut of K elements. A complete graph has no vertex cut. In fact, the only graphs which do not have vertex cuts are those that contain complete graphs as spanning subgraphs. If G has at least one pair of distinct non-adjacent vertices, the connectivity K of G is the minimum K for which G has a K vertex cut. Otherwise, we define K of G to be V minus 1. Thus, K of G equal to 0 if G is either trivial or disconnected. G is said to be K connected if K of G greater than or equal to K. All non-trivial connected graphs are one connected. Next is blocks. A connected graph that has no cut vertex is called a block. Every block with at least 3 vertices is 2 connected. A block of a graph is a subgraph that is a block and is maximal with respect to this property. Every graph is the union of its block, which is illustrated in the example given here. In this figure, subdivision A represents the graph G and subdivision B represents the blocks of the graph G. Graph G actually consists of about 11 vertices, and in subdivision B, you can see the blocks of the graph G, and there are about 8 blocks. Now moving to one of the applications, namely construction of reliable communication networks. If we think of a graph as representing a communication network, the connectivity or edge connectivity becomes the smallest number of communication stations or communication links whose breakdown would jeopardize communication in the system. The higher the connectivity and edge connectivity, the more reliable the network. From this point of view, a tree network, such as the one obtained by Driscoll's algorithm, is not very reliable. Now we have to discuss some simple methods for constructing some graphs whose connectivity number and the number of vertices is given. Such a graph is denoted by Hmn, where m is the vertex connectivity number and n is the number of vertices. That is, Hm, is an m-connected graph with n vertices. Moving to the construction of such Hmn, there exist 3 cases. The first case where we will consider m as an even number. Then we can write m equal to 2r. Then H2r, n is constructed as follows. It has vertices from 0 to n minus 1 and 2 vertices I and j are joined if I minus r less than or equal to j less than or equal to I plus r, where addition is taken modulo n. In case 2, we will consider m as an odd number and n is even. Let m equal to 2r plus 1. Then h2r plus 1, n is constructed by first drawing h2r, n and then adding edges joining vertex I to vertex I plus n by 2 for 1 less than or equal to I less than or equal to n by 2. In case 3, m is taken as odd and n is both m and n are odd. Let m equal to 2r plus 1, then h2r plus 1, n is constructed by first drawing h2r, n and then adding edges joining vertex 0 to vertices n minus 1 by 2 and n plus 1 by 2. And vertex I to vertex I plus n plus 1 by 2 for 1 less than or equal to I less than n minus 1 by 2. Next is Euler tours. A trail that traverses every edge of the graph G is called an Euler trail of G. A tour of the graph G is a closed walk that traverses each edge of G at least once. An Euler tour is a tour which traverses each edge exactly once. In other words, a closed Euler trail. A graph is Eulerian if it contains an Euler tour. Next is a theorem. A non-empty connected graph is Eulerian if and only if it has no vertices of odd degree. In the proof, first let G be Eulerian and let C be an Euler tour of G with the origin and terminus U. Each time a vertex V occurs as an internal vertex of C, two of the edges incident with V are accounted for. Since an Euler tour contains every edge of the graph G, the degree of V is even for all V not equal to U. Similarly, since C starts and ends at U, degree of U is also even. Thus, G has no vertices of odd degree. Conversely, suppose that G is a non-Eulerian connected graph with at least one edge and no vertices of odd degree. Choose such a graph G with as few edges as possible. Since each vertex of G has degree at least 2, G contains a closed trail. Let C be a closed trail of maximum possible length in G. By assumption, C is not an Euler tour of G, and so G minus E of C has some component G dash with E of G dash greater than 0. Since C is itself Eulerian, it has no vertices of odd degree. Thus, the connected graph G dash also has no vertices of odd degree. Since epsilon of C dash greater than epsilon of C contradicting the choice of C. Hence, the G should be an Eulerian graph. Now, these are some problems from the topic that we have discussed. Try to do it by yourself. Thank you.